The MCAT Podcast, session number 155. A collaboration between the medical school headquarters and Next Step Test Prep, the MCAT Podcast is here to make sure you have the information you need to succeed on your MCAT test day. We all know that the MCAT is one of the biggest hurdles you'll face as a pre-med, and we're here to give you the motivation and information that you need to know to help get you the score you deserve so you can one day call yourself a physician. Welcome to the MCAT Podcast. My name is Dr. Ryan Gray, and as always, I'm joined by Clara from Next Step Test Prep to give you the best MCAT advice in podcast form there is. If it's been a while since you've shared this podcast with a friend, a classmate, an advisor, can I ask that you do that? Post it on social media, email your advisor, post it, print out a paper and post it on the bulletin board at school, whatever you need to do. Share this podcast with your friends. Remember, collaboration, not competition, is key to your success. This week, we have some more high-yield topics talking about light, optics, and more physics high-yield topics. Clara, back for some more MCAT podcasts, some more high-yield topics. I hope that this week is better than last week and I get some answers right. Although I like being wrong because then you can explain to me why I'm wrong, and that's where the students learn, right?
Oh, yeah.
So I'm wrong for you guys.
Yeah, every wrong answer is a opportunity. And
to further expand that, as we talked about in our review episode a few weeks ago now, every right answer is an opportunity to learn as well. That's why you have to review both of them.
Absolutely.
All right. We have another high yield topic today, physics, light and optics. Now, for some students, you say physics and they go into a corner and rock back and forth. For me, I loved physics. It was a very tangible kind of science where a lot of it's based on math and just something that the way that my mind worked, I could just see things. And so hopefully, I doubt I remember any of this, but hopefully for some students, even if they're the ones that want to go run and hide from physics, we can give them a little bit of courage and some motivation to know that they can do it as well.
Absolutely. Yeah, this actually, so I was a rocking in the corner type of physics student. And especially for like light and optics, actually optics was the number one topic that I was terrified was going to come up on my test. So
why was that?
Oh, it's funny. I mean, so the first time I took the MCAT, I took the old MCAT in 2014. And I don't know, I guess students weren't really as used to like this whole concept that, optics, like it's just really highly relevant to the eye. Like, it's going to be this really cool, like physiological context. And like once I learned it that way later, it made total sense. But when I was just thinking of it like, oh, like I've got to like draw a ray diagram. And it's I just thought of it very like based on hardware and not physiological. It just was kind of boring. And so,
and so as soon as you made the switch in your mind that this is relevant, you had more fun with it.
Absolutely.
Okay. That's something good that hopefully students can keep in mind. And that's definitely something that I struggled with in medical school, even learning histology and biochemistry in medical school. I'm like, I want to be an orthopod and cut bones and put bones back together. How is this relevant? And that mindset definitely hurt me. And so for the student, if you're having those mindset issues as well, just remember that a lot of this stuff is completely relevant to what you're doing. Not maybe specifically the topic. There are some topics where you're like, oh, I'm never going to use this again in medical school and beyond. And that's true. There are some of those topics, but the relevance is all about your ability to learn and to integrate knowledge and to really overcome the questions. So think about it in that way.
Totally. Yeah. Everything's on there for a reason.
Yep.
It's not random.
Yes. All right. I'll let you start with question 7 here.
Okay. Question 7. Yellow light has a wavelength of 570 nanometers. Which of the following has a higher frequency than yellow light? A, orange light, B, infrared light, C, X-rays, or D, radio waves?
Mm-hmm. So this one to me is you either straight up know it or you don't, which makes it hard. And so I'd have to remember kind of that color scale and what the wavelengths for each of the colors. Does it go kind of right to left, left to right to know if orange is higher or lower? And then infrared, X-rays, and radio waves is, again, just going to be something that the student's going to know or not know. And so obviously it sounds like, for just kind of diverging off of the question here for a second, it sounds like high yield for physics and light and optics is to know, kind of similar to knowing amino acids and knowing the structure and the 3-letter and the 1-letter and all of that stuff. It sounds like students should kind of be aware of wavelengths for different light waves and radio waves.
Yeah, so this is the whole like electromagnetic spectrum, which essentially is like that whole, from high frequency to low frequency, whereas visible light, whereas infrared, that absolutely comes up all the time.
Okay. So definitely a good high yield thing is to be able to sit down and draw these out and kind of plot them out on a wavelength spectrum.
Yeah, definitely. Basically, all you really need to know for this is like to just have a sense of the order. So, whereas orange light compared to infrared, compared to X-rays, you definitely don't need to memorize like any concrete numbers around it, except for visible light falls between 400 and 700 nanometers. But that's like literally the only number you need to memorize. Everything else is just relative positioning.
Okay. And so this is potentially maybe just something that popped out into my mind with what you said, to say, hey, visible light is between 400 and 700. And then I'm like, well, if visible light is between 400 and 700, does that mean like infrared light is above that because it's higher? But what about X-rays and radio waves? Do those count as higher because we can't see them, or are they lower? And so I'm confused. And so the thing that popped in my mind was, well, wait a minute. One is saying wavelength and one is saying frequency. And so you have to make that kind of translation in your head to say, okay, higher frequency typically means shorter wavelength, does it not?
Yes, you're correct.
Okay. And this is where students think that the MCAT is trying to trick them, and why we always focus on critical thinking and analysis and reading comprehension, right? So a student trying to rush through this section will go, oh, yellow wavelength, yellow light wavelength 570, which has a higher wavelength than yellow light, and they'll jump to the answers. And they won't read higher frequency, which means shorter wavelength. And so they'd get the question wrong just because of that. So you have to be careful and translate that in your head. So lower frequency or lower wavelength than 570. I would guess orange light, but I don't know for sure.
Orange light actually has a slightly higher wavelength.
Darn it. All right.
So close though.
Okay.
Yeah. So this one, okay. So first of all, you're totally right about being careful. And I always like to say, like, the MCAT isn't actually trying to trick you. It's just rewarding careful reading.
Yeah.
Right. Like, as long as you just read every word and understand every word, then you're sort of gold. But the second you miss a word, then then you'll get it backwards. So basically with this one, the answer is C, X-rays.
Okay.
And one trick that I've always found to be like totally foolproof when it comes to the electromagnetic spectrum is that if you just remember that higher frequency corresponds to higher energy, it typically is a lot easier to figure out like which types of light are higher energy, because a lot of times these higher energy, higher frequency light are more damaging. So like, for example, at the very high frequency end of the electromagnetic spectrum, we have gamma radiation. And gamma radiation is super damaging, can cause all of these problems to DNA and to human physiology in general.
I've watched Chernobyl. I'm an expert on radiation now.
Yeah, scary stuff. So gamma rays are at the very high frequency end, and then X-rays are relatively up there as well, because X-rays, if not administered carefully, can also be very harmful to DNA. So that's how I like to remember that, okay, like gamma rays, X-rays, and even like ultraviolet, like the sunlight that damages our cells, those are all on the higher frequency end of the spectrum.
Okay.
So C is the only one of them that's listed.
Okay. So it's interesting. So when I see that, I used to watch a lot of the like superhero TV shows, and the Flash always sticks into my mind. And when you said that about the higher frequency is more damaging to our bodies, to DNA, etc., I picture a scene where the Flash like vibrates his hands super fast, like really high frequency, and can like reach into a body and like take your heart out and stuff. So so hopefully that visual will help a student with their MCAT.
Oh, totally. Yeah.
All right. So high frequency damaging, and so going through that is radio waves damaging. I would hope not, because we're bombarded with radio waves all the time. X-rays, right? We think of as damaging because we put on lead aprons and protect ourselves from those when we need to get X-rays.
Exactly.
Okay. Very cool. Question 11. Which changes are experienced by visible light as it moves from medium 1, n of 1.16, to medium 2, an n of 1.68? All right. A, wavelength remains constant while frequency decreases. B, wavelength decreases while frequency remains constant. C, wavelength decreases while frequency increases. Or D, wavelength increases while frequency decreases. Ooh. All right. So this is the one that always tricks me, because I always forget there's one of these that remains constant as it goes from medium to medium, right?
Yes, you're right.
Okay. So the question is, which one is it? Wavelength or frequency? And so knowing at least part of that, or knowing that one fact, would give me a 50% chance, because C and D, both things are changing, and we know that isn't true. But A and B, wavelength remains constant, and B, frequency remains constant. And so let's think about these things. And so you were talking earlier with the last question about like X-rays and gamma radiation. They're really high frequency. And so something tells me that just because we're changing mediums, it's not going to change a gamma ray into an X-ray, because it's decreasing its frequency, its damaging part. And so frequency to me seems like it would make the most sense to remain constant based on just our talk 2 seconds ago. So I would go with B.
He's correct.
All right.
Nice. Yeah, so frequency does remain constant, and yeah, I mean you're right. Like the identity of a type of radiation isn't going to change just because it moves into a different medium. And then otherwise, you kind of just have to have this memorized. Like one easy way to remember that something has to remain constant is just to think about the simple equation that's like velocity of a wave equals wavelength times frequency. And when we move into a different medium, the velocity of the wave changes. Like in this case, it moves into a medium with a higher index of refraction, so it's going to slow down. Mm-hmm. And if velocity slows down, something else will have to decrease, but the other thing can't like correspondingly increase like we typically think. So yeah, so it has to be A or B. Beyond that, you kind of just have to remember, okay, frequency is not ever going to change. Frequency doesn't fluctuate. Exactly. There you go. Some alliteration for you. Or you could say wavelength waivers. Yeah, that's a good one. Yeah. All right. All right. So frequency. Get that in your head, that frequency doesn't change medium to medium. All right. At least I remembered that probably from an MCAT podcast a long time ago. Yeah. A lot of students don't know that. So yeah. All right. Question 14. All right. 14. Of the situations below, which is least likely to lead to total internal reflection? A, visible light moves from diamond, which has an N equal to 2.4, to air, N equals 1.0, at an angle of incidence of 81 degrees. B, visible light travels from diamond to air, same N values, at an angle of incidence of 46 degrees. C, visible light travels from water, N equals 1.34, to air at an angle of incidence of 81 degrees. Or D, visible light travels from water, N equals 1.34, to air at an angle of incidence of 46 degrees.
Oh. And so this one to me, again, trying to put myself in the shoes, it's not very hard, into a pre-med who may have forgotten to study this. I'm like, oh, okay, this is easy. Let me just think through this, right? Diamond, I can picture a diamond and looking through a diamond, and I can picture water, and what's going on there. The tricky part here is least likely to lead to total internal reflection. So that's, again, making sure that you're reading every word appropriately. Just make sure that you know that this is a least likely one. And so least likely to lead to total internal reflection. And so to me, just to understand the definition here, total internal reflection to me means that the light is not escaping at all.
Exactly.
So that to me would mean if I'm on the other side, right? If I'm in the air, then I can't see that light coming from the water or coming from the diamond. And so if I'm thinking about it, if I'm above the water, can I see, if the water's clear enough, can I see the fish below? And the answer is yeah, I can for the most part. Now the question is the angle of incidence, the 81 or 46. Does that matter? Potentially, maybe, but we'll leave that for now. So C and D right now potentially are not least likely. A and B. So diamond is interesting. So diamond we think of as relatively clear. So I, again, just kind of trying to make it as easy as possible for my brain, almost thinking of it kind of like glass, even though obviously I know it's not. But looking through a diamond, we can definitely know that some things go through and some things don't. Diamonds are definitely interesting. There's lots of stuff bouncing around in there. And so for me, it's either A or B. And then the angle of incidence, the shallower angle of incidence, I think would be shallower, the 46 degrees. To me makes it more likely to be reflected. For some reason, that just seems to make more sense. So I'd go with B, but I don't know. That's as far as I can get thinking through it.
Yeah. There's a lot going on here. But yeah, so the answer here is actually D.
Oh, all right.
So yeah, so the 46%, the 46 degree part, I think you got right. And the diamond versus water part was tricky. And the thing about optics is, even though it's easier to picture in our heads than some of this other MCAT science, it's kind of tricky to picture like real life optics like this happening, because in real life, we actually have light rays coming from like all directions, like all different angles. And so we can be like, oh, we can see some light shining through diamond. We can see light shining through water. So like we have no clue what the right answer is. So we need to know a little bit more about total internal reflection to like really make sure that we get this one right. And so basically, so total internal reflection is where a light ray going through a medium hits an interface between that medium and another medium, and it doesn't leave. So it essentially, like you said, like it's stuck in the original medium. And this tends to happen when there's a really big difference between the index of refraction of the first medium and the second one. because the bigger the difference between the index of refraction, which is like those n values that we mentioned, the bigger the difference, the more the light is going to bend when it hits that border. And if it bends enough, it can actually bend all the way. So it's like bending back, pointing in toward the medium itself. So here we see for A and B, the diamond and air ones. Diamond had n equals 2.4, air had n equals 1.0. So that's a really big difference. So that is likely to undergo total internal reflection, and A and B can be eliminated. So that's why it had to be one of the water ones, because there's a smaller difference.
Okay.
Yeah.
Just a quick question as I'm reading this. A says visible light moves from diamonds, and the other ones all say visible light travels. Is that just a typo kind of thing, or is there significance there?
There's no. It could have said either. That's actually. I'm glad you pointed that out, but no, I can't imagine there would be any scientific meaning.
Okay.
Yeah. No, but it is good to analyze every word, but
every word.
Every word. Yeah, so that one's that.
Okay. And so talk about the angle of incidence then. So we know that 2.4 to 1 is bigger, so those are out. And then what's the angle of incidence? How does that play into it?
Totally. So in optics, the angle of incidence is referring to the angle it makes. Essentially, here I'm actually drawing this one out. And if you have pencil and paper, it can really help to draw out optics questions. But basically, what this is saying with this angle of incidence of 81 degrees, that means it's coming in with an angle of incidence of 81 degrees to the normal. So what that means, if you actually picture it in your head, is it's coming in with this very, very large angle of incidence, meaning it's almost parallel to the border between the diamond and the water, or between the diamond and the air, or the water and the air. So it's coming in, already has this really big angle. It's already almost parallel to the surface of that water, that diamond. And it only needs to bend a little bit when it hits that surface to actually be pointing back in towards the diamond or towards the water. Whereas the 46 degree has a smaller angle of incidence. And so it's coming in about about halfway between the normal and that border. And so it will have to bend essentially all the way around to bend back into the medium. And that's just sort of a long-winded way of saying total internal reflection is much, much more likely when you have a large angle of incidence. So here, since we're asked this least question, we want to pick the one with the smaller angle.
Okay. So total internal reflection is more likely when there's a larger difference between those n values, and it's more likely when the angle of incidence is larger as well. Exactly. Okay. So think large with total internal reflection. All right. So there you have it. Some high yield physics for you. Hopefully you got some good tips and tricks that are going to help you crush the MCAT. If you are looking for some full-length exams to prepare for the MCAT, which is the best way to prepare for the MCAT, don't forget to check out Next Step Test Prep. They have, if you go and ask pre-med students anywhere, SDN, Reddit, the pre-med Hangout, 90+% of them will tell you that Next Step Test Prep has the second best MCAT full-length exams. And you go, wait, Dr. Gray, the second best? Why do I want the second best? Well, that's because first best is the AAMC, of course. The people who make the MCAT, they sell their own version of full-length exams, practice exams, but they only sell 3 of them that are scored. They have one unscored one as well. And many students need more than those 3. And that's where Next Step Test Prep comes in. They have up to 10. You can get 10. You actually get 1 for free. You can go sign up. nextsteptestprep.com. Get a free diagnostic and the first full length out of their 10 that you get for free. If you need some more, you can buy. Use the promo code MCATPOD to save 10% on those full lengths. Hope you have a great week. We'll see you next time here on the MCAT Podcast.
This is MedEd Media.